Hello everyone, welcome to this series of lectures on the course Foundations of Mathematics. In this lecture, I will talk about composition of functions. Now, supposing I have two functions, the first function f, let's say from the set x to the set y, let's say this is y, and I have a function f from the set x to the set y, and I have one more function g from the set y to the set z. So this is my set z and g is a function from y to z. Okay, so if I pick up any point in the set x, let's say small x, then it will have an image under the function f in the set y. So the point f of x will be lying here, right? So f of x is a point in y and g is a function from y to z. So this f of x will have an image inside z through the function g, right? So I will have a point here which is g of this point f of x, right? So to each point in x, I can find a point in z which is associated to this point in x, right? So if I start with a point x in x, then I can relate it to a point g of f of x in the set z. So I can do this for each and every point in the set x. So I can define a function from the set x. So this function from x to z, I will call it as g composite f. Okay, and that's called the composition of the functions f and g, and it is defined to be g composite f of any point in the set capital X is defined to be the point g of f of x, which is a point in the set z. Okay, so this is called composition of functions f and g. Now if you see, the codomain of the first function f is the domain of the second function g here, right? That's the set y, which is common in both the cases. So formally defining, let f from x to y and g from y to z be two functions, then the composition of f and g is the function g composite f from the set x to the set z defined by g composite f of x is equal to g of f of x for each x in x. So this map is defined for every point in the set capital X, right? Now this G composite f is sometimes also referred to as GOF. Okay, you can also call it as GOF. Now if the codomain of the set f and the domain of the set G are not equal, then can I still define the composition of the two functions f and g, that is G composite f? Will that be possible? Yes, provided the image set of the function f, that is f of capital X, is completely lying in the domain of G. Okay, so let me put that down as a remark. If f is a map from X to Y and G is a map from Z to WC, such that range of f is contained in the set Z, that is the domain of the function G. Okay, then G composite f is well defined. Okay, then we can talk about the function G composite f. So it's not necessary that these two sets have to be equal. Okay, it's enough that the range of f is entirely contained inside the domain of G, and if that happens, then I can talk about their composition, that's G composite f. All right. Now moving on to some examples. Look at these two functions. Let f and g be functions from R to R defined by f of x equal to x cube and g of x equal to 2x plus 5. Compute G composite f and f composite G. Now let's see, f is a map from R to R and G is a map from R to R again, right? So these two are equal here. So I can talk about G composite f, and that will be a map from again R to R, right? And how will that be defined? So G composite f of x, or of G of f of x is G of f of x, but f of x is given to be x cube, so that's x cube, and g of x is 2x plus 5, so g of x cube will be 2x cube plus 5, and that's G composite f. All right. Now G is a map from R to R, and f is also a map from R to R, right? So f and the codomain of G is same as the domain of f, so I can talk about the function f composite G, which will be from R to R, right? So f composite G is a map from R to R, and f composite G of x is defined to be f of G of x, but G of x is nothing but 2x plus 5, so that will be f of 2x plus 5, and f of any point, f maps any point to its cube, so f of 2x plus 5 would be 2x plus 5 the whole cube, right? So this is G composite f and this is f composite G. From here it's clear that they are not equal. Okay, so in general f composite G need not be equal to G composite f. Okay, in some cases they are equal, but in general you cannot say that f composite G will be same as G composite f. All right, one more example. Consider the functions f from R to the interval 0 infinity closed at 0 defined by f of x equal to x square, and a function g from the interval 0 infinity closed at 0 to R defined by g of x equal to root x. Okay, so here this root x is the unique non-negative square root of x, because the domain of G is not having any negative numbers. This root x is well defined here, right? So I want to talk about f composite G and G composite f. So let's see whether they are defined or not. Now f is a map from R to 0 infinity, and G is a map from 0 infinity to R, right? So the codomain of f is same as the domain of G. So G composite f will be a map from R to R, right? So that's a map from R to R, and if you look at, no, let's compute G composite f first. So G composite f of x is, it is defined to be G of f of x. So this is nothing but G of f of x is x square, so that's G of x square, and G maps every point to its square root, so this would be square root of x square, which is mod x. Now talking about f composite G, G is a map from 0 infinity to R, right, and f is a map from R to 0 infinity. So the codomain of G is same as the domain of f, so I can talk about f composite G, and that will be a map from 0 infinity to 0 infinity, right? So from here I can see that the domain and codomains of G composite F and F composite G they are different. The domain of G composite F is R, whereas the domain of F composite G is 0 infinity. So from here itself I can conclude that G composite F and F composite G are not equal, right? Because we say that two functions are equal only if their domains are same, their codomains are same, and they agree at each and every points in their domains. So F composite G of F G of X is F of G of X, but G of X is root X, so that's F of root X, and that's root X the whole square, which is X, right? So, but in general, F composite G is not equal to G composite F. This is because their domains are different. They have different domains, and hence these two functions FOG and GOF are not equal. Okay. Next, I'll leave this as an exercise for you all to try. Supposing f and g are two functions from R to R defined by f of x equal to x cube plus 2 and g of x equal to cube root of x, then compute f composite g and g composite f and check whether they are equal or not. Okay, so see that you all do this. I will leave this as an exercise. Next, consider this example. Supposing I have a function f from the set of natural numbers to the set of rationals defined by f of any point in n, that is f of any natural number is that natural number by 4. Okay, let's define f as this, and supposing g is a map from z to z, and let's say g is an identity function, g of any integer, let's say y is y. Then can I talk about the composition of f and g? That is the question. Okay, or I can pick up this to be the set of natural numbers. Yeah, let's keep it this way. Now f is a map from n to q and g is a map from n to z, right? Now what is range of f? Is range of f contained inside the set of natural numbers? No, because if you pick up f of, let's say, 5, that would be 5 by 4. So the point 5 by 4 will come in the range of f, which is not a natural number, right? But G composite f is not defined as range of f is not contained inside the set of natural numbers. So you can give an example here. The point 5 by 4 belongs to the range of f, but 5 by 4 is not a natural number, right? So I cannot talk about G composite f. Okay, so this is an example of two functions wherein you cannot talk about their composition. Okay, now let's look at some theorems related to composition of functions. If I take two 1-1 functions f and g such that their composition is well defined, then their composition G composite f is also 1-1. Okay, so if f from x to y and g from y to z, they are 1-1, they are functions. If they are 1-1, then their composition G composite f is also 1-1. This is what we need to prove, right? So our claim is to show that G composite f is 1-1. So supposing this is f from the set x to the set y, and let's say I have g here from the set y to the set z. So I want to show that G composite f, which is a map from x to z, is 1 1, right? So supposing I will use the proposition that we have done under 1 1 functions. Suppose G composite f of x1 is same as G composite f of x2, where x1 and x2 are points in x. Okay, so x1 and x2 are here, and I'm talking about G composite f of x1, which is same as G composite f of x2. Okay, I want to show that x1 is equal to x2, right? So if we are able to show that x1 equal to x2, then we can say that the map G composite f from x to z is also 1 1, right? So by definition, G composite f of x1 is G of f of x1, and that is equal to G of f of x2. So G of this point f of x1 is same as G of this point, but G is given to be a 1 1 function, and G of f of x1 is G of f of x2. So this implies f of x1 is equal to f of x2, right? This is since G is 1 1. So those 2 points will be here, f of x1, and that is same as f of x2. Okay, that's because G is 1 1. So f of x1 is equal to f of x2, but f is also given to be 1 1. This implies x1 is equal to x2. This is since f is 1 1, right? So if f and g are 1 1, then G composite f is 1 1. That's what we showed. So this implies G composite f, which is a map from x to z, is 1 1. Okay. So composition of two functions, of two 1 1 functions, is again 1 1, provided it is well defined. Okay. Second one is a similar one for onto functions. If f and g are onto functions, then their composition G composite f is also onto, provided it is well defined, of course. So if this is your set x and f is a map from, let's say, x to y, and g is a map from y to z. Okay, and I'm talking about the composition from x to z, that's GOF. So we want to show that our claim is G composite f is onto. It's a map from x to z. We want to show that it is onto. So how do we show that it's a map? How do we show that a map is onto? You start with a point in the codomain of that function, and we have to find a pre-image for that, right? So let's pick up one point in z. Let P be a point in z. So we have to find one point in x which is mapped to this point P by the function G composite f. Then I can say that G composite f is a onto function, right? So we have a point P inside z here, but G is a map from y to z, and G is given to be onto. So I can find a point in y which is mapped to the point P through the function G, right? So since G is onto, there exists a point Q in y such that G of Q is equal to P. So I can find one point here, that's Q, such that G of Q is P. Okay. So then I end up with a point in y, that's Q. But f from x to y is also given to be onto, right? So I can find a pre-image for the point Q. So since f is onto, there exists some point, let's say M, in X such that f of m will be equal to q. So I can produce a point m here such that when you look at f of m, that will be exactly equal to q. Fine. So I can write that q. I just erase that q and I'll write it here. Yeah. So that's the point q. So finally, what we have is g of q is equal to p and f of m is equal to q. Right? Then what is G composite f of m? Then G composite f of m is nothing but G of f of m, but f of m is nothing but q, so that's G of q, right? But G of q is equal to p. That means G composite f of m is equal to p. So what we did is, for any point p in z, we produced a point m in x such that G composite f of m is equal to p. That means every point in the set z has a pre-image in the set x under the function G composite f. And this tells us that the function G composite f is onto. Alright. So if I have two onto functions, then their composition is also onto, provided it is well defined. And I can combine this result with the previous one to conclude that if two functions are bijective, then their composition is also bijective. Okay. So since f is 1 1, since f and g are 1 1, G composite f is 1 1. This is by the first result, that's by 1. In the same way, since f and g are onto, G composite f is also onto. This is by 2, right? So from this I can conclude that G composite f is bijective. So if two functions are bijective, then their composition will also be a bijection, provided it is well defined. Clear? The next question that arises is the converse of these three statements true? That is, if G composite f is 1 1, then can I say that both f as well as g are 1 1? Second, if G composite f is onto, then can I conclude that both g as well as f are onto? And if G composite f is a bijective function, then can I conclude that f and g are both bijective? So these questions we are going to answer now. So looking at the first one, if G composite f is 1 1, then f will definitely be 1 1. Okay, and we cannot say anything about G whether G is 1 1 or not. It may or may not be 1 1, but f is definitely 1 1, and that's what we will prove now. So let f from x to y and g from y to z be functions. If G composite f is 1 1, then f is definitely 1 1, and we cannot say anything about the function g. Okay, so supposing this is the set x, this is the set y, and this is the set z, and f is a map from x to y and g is a map from y to z, and then we have f G composite f, which is a map from x to z. So I want to show that f is 1 1. Okay, so let f of x1 be equal to f of x2, where x1 and x2 are there in the set capital X. Okay, so I will start with 2 points here, x1 and x2, whose images are same. Okay, such that f of x1 is same as f of x2. We need to prove that x1 is same as x2. Okay, Now f of x1 and f of x2, that point f of x1, which is same as f of x2, is in y. Okay, and G is a map from y to z, so I can talk about their images, and their images will also be same because G is a function, right? So that's the single point here, and it cannot be mapped to two different points. So G of f of x1 will be same as G of f of x2, right? And that is same as saying G composite f of x1, because that's how G composite f is defined, is same as G composite f of x2. But G composite f is given to be a 1-1 map, and G composite f of x1 is equal to G composite f of x2. This implies x1 is equal to x2, and this is since G composite f is 1-1, right? So if f of x1 equal to f of x2, then I can say that x1 is equal to f x2, and that tells us that the function f is 1-1. Okay, so I cannot conclude anything about the function g here, and that I will leave it as an exercise. Find functions f from x to y and g from y to z such that G composite f is 1-1, but f composite G is not 1-1. Okay, so you have to construct a function f from x to y, g from y to z, where x and y can be any sets, and you have to define the functions f and g such that G composite f will be 1-1, but no, that's I made an error here, but f is not 1-1. Okay, G composite f is 1-1, but not f, sorry, G. That has to be G, but G is not 1-1. Okay, we showed that this function f is definitely 1-1 from here, but this function g need not be 1-1. Okay, so this you'll have to construct an example which satisfies this. Okay, so that I will leave it as an exercise. Moving on to the next one. If g composite f is onto, then g will definitely be onto, and I cannot say anything about the function. Okay, so we will assume that g composite f is onto, and we will show that the function g is onto. Okay, our claim is g is onto. So let me draw the sets. Supposing this is the set x, and supposing f is a map from x to y, and g is a map from y to z. Okay. Yes. Now we want to show that g is onto. So let's start with the point in z. Uh, let's say k belong to z. Okay, so I'm starting with the point z here. I have to find a point in y, okay, which is mapped to this point, not z, that's k, which is mapped to the point k through the function g. Okay, I have to produce a point in y. But g composite f is given to be onto, and that's a map from x to z, right? So since G composite f is onto, there exists a point n in x such that G composite f of n will be equal to k, sorry, right? G composite f is a map from x to z, and that is onto. That means every point in the z will have a pre-image. So I can find a point n here such that G composite f of n will be k, right? But this implies how G composite f is defined. G of f of n is equal to k. And where is this point f of n? If n is there in X, then f of n will be in the codomain of F, and that's why. So the point f of n is here. So what we have done is, given a point K in Z, we have found a point f of n in Y such that g of f of n is equal to K. Okay. So you can give some name to this. Let's say P. So you can call this P. Therefore, there exists P equal to f of n such that g of P is equal to K. Right, and that tells us that the function g is onto. So if g composite f is onto, then g will definitely be onto. I cannot say anything about if. So again, I will leave that as an exercise. Okay, find. This is an exercise. Find functions f from x to y and g from y to z such that g composite f is onto, but f is not onto. Okay, so f should not have a preimage. All right, so look out for such functions, such sets x, y, and z, which satisfies these two conditions. Okay. Next, this is one more exercise. If f is a function from x to y and g is a function from y to z, such that g composite f is 1 1. Okay, such that g composite f is 1 1 and f is onto. Okay, two things are given to you. G composite f is 1 1 and f is onto. The question is g 1 1? Okay, so if g is 1 1, you'll have to prove it. Otherwise, you'll have to give a counter example for this. Okay, so this again I will leave it as an exercise. So see that you all give a try to solve this one. Okay, a very simple one. So this is an exercise for you. The next theorem says, let f from x to y, g from y to z, and h from z to w be three functions. Then h composite g composite f is same as h composite g composite f. That says composition of functions is associative, provided it is well defined. Earlier, we have already seen that composition of functions is not commutative because f composite g need not be same as g composite f, even though both of them are defined. Right? So we will see now that composition of functions is associative. Okay. So supposing I have a function, let's say f from x to y. Let me draw their domains and codomains. So this is the set x, this is y, let's see, this is z, and this is w. Okay, and I have functions f from x to y, g from y to z, and h from z to w. Okay, now f is a function from x to y and g is a function from y to z. So f is a function from x to y and g is a function from y to z. So from this, I know that g composite f is well defined function from x to z, right? And along with this, h is a function from z to w now. Okay, plus h is a function from z to w. So I can talk about h composite g composite f, and that will be a function from x to w, right? Because the codomain of g composite f is same as the domain of h. So I can talk about h composite g composite f, and that will be a map from x to w, right? So this is one thing. Let me put it in a box. And secondly, now if I look at g from y to z, also g is a map from y to z and h is a map from z to w. So I can talk about each composite G, and that will be a map from Y to W, right? Along with this, what we have, F, which is from X to Y, plus each composite G, which is a map from Y to Z. So the codomain of F is same as the domain of each composite G. So I can talk about each composite G, composite F, and that will be again a map from X to Z, from here to here, right? So each composite G, composite F is a map from X to W. So its domain is X and codomain is W. And each composite G, composite F is also a map from X to, so sorry, this is, I think I made an error here. Yeah, this is from Y to W. Yeah, that's from Y to W, and this is also from Y, X to W. Okay, I made a small error here. I've rectified that. So each composite G, composite F is a map from X to W. So if you compare both, their domains and codomains are the same, right? Now I want to show that each composite G, composite F, this function is same as each composite G, composite F. Okay, and when do you say that two functions are equal? Their domain should be same, their codomain should be same, and they should agree at each and every value in their domains, right? Their domains are same. So here we have already shown that their domains and codomains are same. Okay, so now we only have to show that they agree at each and every value in their domain, right? So let's write it systematically. So F is a map from X to Y and G is a map from Y to Z. So G, composite F, will be a map from X to Z. Okay, and therefore if I club H along with this, then that would be H composite G, composite F, which will be a map from X to W, as we have just seen. I'll name this as 1. Similarly, G is a map from Y to Z and H is a map from Z to W, right? So H composite G will be a map from Y to W, and F is again a map from X to Y, and therefore H composite G, composite F will be a map from, no, this is from Y to W. Sorry, I again made the same error. So that's from Y to W, right? Yes, Y to W. And this will H composite G, now composite F will be a map from X to W. Okay, so therefore their domains and codomains are same. The domains and codomains are equal. Next, we have to show that they agree at each and every value in the set X. If we are able to do that, then we can say that both these functions are equal, and hence composition of functions is associative, right? Start with a point in the set capital X. Okay, so let me start with a point in the set capital X. Let X belongs to capital X. We need to show that H composite G, composite F of X is same as H composite G, composite F of X. Okay, now X is sitting inside the set capital X, right? So let's assume that its image is Y. Okay, and let's call it F of X as Y. So if X is in capital X, F is a map from X to Y. So F of X will be in Y. So this point f of x, which we are calling y, will be in the set y, right? So we have f of x here, so g of that point y will be in z. So let's call that small z. So let small z be equal to g of y, but y is nothing but f of x, so that is actually g of f of x, and that's a point in z, right? So small z is a point in z, correct? Now h is a map from z to w, and z is a point in capital Z. So I can talk about h of z, and let's call that as small h, but small z is nothing but g of f of x. So this is f of g of f of x, right? So this is what we have. So now from this, what will be g composite f of x? Okay, I'm coming to this. So g composite f, let's look at that first. G composite f of x will be g of f of x, right? By definition of composition of functions, g composite f of x will be g of f of x, and that is nothing but f of x is y, so this will be g of y, and g of y is nothing but z from here, right? So g composite f of x is nothing but z. I hope that's clear. Now you compose h with g composite f, and therefore h composite g composite f of x will be h of g composite f of x, but this is z and this will be h of z, right? This will be h of z, because just now we have seen that g composite f of x is nothing but z, so this will be h of z. So I think this h might create a confusion. Let's call this a small w. I think, yeah, that's better. And h of z is nothing but w. So what we have shown is h composite g composite f of x is w. Okay, so this left hand side here is w. Now we need to compute the right hand side and show that it is also turning out to be w. So both of them will be equal to each other. So for that, let's compute h composite g first. Now h composite g of x will be how much? By definition, h composite g of x is h of, no, let's consider y here. So no, yes, that's y. So h composite g of y will be h of g of y by definition of composition, right? But g of y is nothing but z. If you go back, g of y is nothing but z, so this will be h of z, which is w, right? So that's w, and now I need h composite g composite f to get the right hand side. So let's compose this with f, and that will give me h composite g composite f of x I want to look at. So this will be, you can consider this to be one function, so this will be h composite g of f of x, right? But f of x is y, so that will be h composite g of y, which we have just now shown that is equal to w. So this tells us that h composite g composite f of x is same as h composite g composite f of x, and hence this tells us that h composite g composite f is same as h composite g composite f, and therefore these two functions are equal to each other. Okay, so composition of functions is I'm writing f in two different ways sometimes. Okay, just take a note here that this f is same as this f. Okay, so from here we conclude that composition of functions is associative. All right, these are my references. Thank you.